Good evening, respected faculty and students at Banasthali Vidyapith and especially the Department of Chemical Engineering. Thank you for your invitation for me to speak to you a little bit today about a topic of interest for a very important day referred to as the Ozone Day. I'll be speaking to you in the next few minutes or so, maybe about 20 minutes or so, regarding this very important development that took place that affects all of us, and actually especially the engineers amongst us. Let me explain to you why this is important. First and foremost, I think you all are exposed to and aware of the issue of climate change. Climate change refers to the impact on the atmosphere that we as humans have been causing through our development, and especially since the Industrial Revolution, and even more so over the last 30 to 40 years or so. This climate that we speak about is in fact the effect of the behavior of that atmosphere. That atmosphere actually goes all the way, almost 10,000 kilometers from the surface of the earth, but what really matters to us is the very thin shell that is around the surface of the earth, consisting of the troposphere, which is about 12 kilometers, and then also the stratosphere, which goes to about, I would say, 50 kilometers or so from the surface of the earth. Now, this thin layer is affected by all kinds of things, including volcanoes, forest fires, and many other emissions that come from the surface of the earth. And a lot of these emissions are such that they essentially create what's called a greenhouse effect, which is that they trap the heat that we get from the sun within that stratosphere and the troposphere, thereby warming the planet, and therefore it's called the greenhouse gas effect. That leads to a whole set of issues caused mainly due to the emissions of carbon dioxide, nitrogen oxide, methane, and a few other greenhouse gases that are generated by mankind. It is in fact very clear that the emissions that were causing a sudden rise in the average temperature of the climate of the troposphere and the stratosphere was mainly due to the sudden increase in emissions that came from human activity. And that is proven beyond doubt by the International Panel on Climate Change, even though there are some naysayers and doubters out there in the world, I guess similar to the people who were claiming that the earth was flat. But be that as it may, what's important to recognize is that there is that whole set of problems related to global warming. But then there's something else. You see, between the troposphere and the stratosphere is a very thin layer, about 3 to 4 kilometers or so, which is composed mainly of ozone, which is O3, as you all know. This ozone layer is particularly important because it traps or it reflects the ultraviolet rays that we get from the sun, rays which are in the bandwidth of UVA and UVB, and of particular importance is UVB. Now, what happens is that as these rays don't reach the surface, we actually don't realize the importance that this ozone layer plays. But what we do know is that whenever human beings or other beings on the surface of the earth are exposed to UVB rays, it leads to skin cancers, and they are aggressive skin cancers. So therefore, it is important to make sure that the ozone layer is not depleted, certainly not because of what we do. If it happens naturally, then we have to think about it differently. But if it is because of what we do, then maybe it's time to look back and change how we work and how we do not generate those gases which are called ozone depleting substances, or ODSs, which cause the depletion of the ozone layer. Now, these are essentially complex compounds, the ones that are emitted due to our activity on Earth. They are, in essence, CFCs, or chlorofluorocarbons. They are, in effect, hydrofluorocarbons. They are hydrochlorofluorocarbons, essentially. And these affect the atmosphere in a very peculiar way. What happens is, when the CFC molecules, or let's take CFC as an example, when they reach the ozone layer, they essentially look at the ozone layer, which receives all the ultraviolet rays, which then enable the ultraviolet rays to split the chlorine atom from the CFCs. So the CFCs go up into the ozone layer, they receive the ultraviolet rays, and the chlorine gets split out of the CFC molecules. And the chlorine atom then breaks up the ozone molecule, and therefore it leaves you only with chlorine monoxide and oxygen, no ozone. And that sort of creates what's referred to in common parlance as the ozone hole. Now, this was suspected sometime in the 1970s, when people started feeling that we seem to be generating and using these quite a bit. And does it in fact have an impact on the ozone layer that's up in the atmosphere? Until 1985, the scientific proof wasn't fully established that in fact there is this effect on the ozone layer. And suddenly then, due to the research that was led by people like Sherwood Rowland, Mario Molina, and Paul Crutzen, all these scientists gave plenty of evidence to show that in fact the ozone layer was depleting. It was depleting mainly around Antarctica, and in fact the size of the ozone layer had become the size of Antarctica, which is a huge continent. Now imagine if that kept on growing, and in fact some scientific evidence pointed out the fact that for every 1% increase in the ozone layer size, the incidence of cancers would increase by 4%. And this is dramatic. We simply can't afford to have that, otherwise life as we know it on the earth would change. This was 1985 when this evidence came to light. And when that happened, suddenly there was all kinds of concern in the scientific community. There was a lot of effort to, especially by the United Nations Environment Program, to raise the awareness of governments, companies, and other people to say, look, we've got to solve this problem. And this is a global problem. It's not restricted to only one or two countries and so on. Now, as a quick history of that, after 85, a lot of people did move together very aggressively. And in 1987, long before the 1992 Rio conference, which acknowledged the role of greenhouse gases, but in 1987, the Montreal Protocol was signed in Canada to try and reduce the production and the consumption of these greenhouse gases in our daily lives. Now, what are these greenhouse gases used for? They are used, for example, CFCs, the chlorofluorocarbons, are used in aerosols, refrigerants, and solvents. In fact, so are hydrochlorofluorocarbons. They are used in many aerosols, refrigerants, and solvents. There's a category of chemicals that you would know as halons. Halons are used in fire extinguishers. We have no other replacement for halons right now. And in fact, other chemicals like, say, methyl bromide, also affect the ozone layer, and they're used in pesticides. Imagine all the agricultural land in the world which uses pesticides. If they have methyl bromide in there, that all those emissions are going to go up and affect the atmosphere and especially the ozone layer and cause the ozone hole. So through major leadership through the United Nations Environment Programme and especially their director, Dr. Mustafa Tolba, there was a lot of awareness building that went on to bring all these parties together. That set the trend. The Montreal Protocol and what it was able to achieve set the trend for all the agreements that have come in international negotiations thereafter, including negotiations related to climate change. But nothing has achieved the level of success and of the Montreal Protocol, which is therefore referred to often as the gold standard in international agreements for environmental protection, and especially, of course, relevant for trying to reduce the effect on the ozone layer. Now, all this is good background, but you as engineers would be wondering, why is this important to engineers? And especially to chemical engineers. You see, they're needed. And there's a reason why. You see, together, all of us, including chemical engineers and other engineers who came before you, controls engineers, process control engineers, civil engineers who built those structures, all the engineering community and others, the lawyers, the scientists, came together to in fact produce these chemicals to meet a certain need. The need that we need to have solvents, that we need refrigeration, that we need aerosols, that we need fire extinguishers, or that we need pesticides. To meet this need, there was all this science, the chemistry, and the energetics behind it that was brought together to create these compounds which helped us suit that purpose, to achieve our goals and to improve our life because of that. But little did we realize the effect on ozone. And this effect, therefore, is a classic effect amongst many others, where society, not just one community or another, but certainly not excluding the engineering community, were responsible for creating things which had what are referred to as unintended consequences. These were unknown, so it's kind of blameless in many ways, but once you know it, it's important to act on it. So maybe it's time that we all as a society cause the problem, but it's also up to society, therefore, to clean that up and to solve that problem. And there again, engineers are needed. Now, this is a very complex problem because the uses are what they would say is ubiquitous. All over the world, these chemicals are being used. In fact, when this problem was recognized, almost over 20 to 30,000 metric tons were being produced every year. And it was important that we bring this down in order to reduce the future impact on the ozone layer. So how do we bring this together? What happened in the Montreal Protocol? Why is that important? For that, a little bit of theory. You see, there was a lady by the name of Elinor Ostrom who put forward this thesis and then ultimately became the first woman to win the Nobel Prize in economics in, I believe it was close to 2007. The concept goes like this. Imagine you produce something, any goods, any services, you produce shoes or bread or whatever, and then you sell it to a person who's willing to pay for it. So you have a single user of that good and you have a willing payer of that good, and there's a transaction and that good is produced and sold and utilized. The organizations that do that extremely well are the private sector, because those industries know how to do that. In the case of that is relevant to our Montreal Protocol, the producers of all these ozone depleting substances, say to name a few, but the big ones, let's say a company like DuPont, which was developing and producing and selling these products were able to sell them to their customers. So a single customer, they would sell it to a customer, they'll get paid for it, and so on. So there was a willingness to pay for that product because it offered a certain service to their customers in turn. On the other hand, those are called private goods because they're supplied and created often by the private sector. On the other hand, are goods that are used by many people, but very few really willingly want to pay for it. And somehow you still have to make that way. You still have to produce those goods. So, for example, a country has to produce its system of defense to defend its borders. It has to produce its system of justice. It has to produce regulations. It has to produce standards which are followed by people, by the public. And there you have many users of those systems. Many people use the systems of justice, systems of defense, and so on. But if you were to ask an individual person to pay for it, that person is going to say, wait a minute, everyone's benefiting from it. I'm not that willing to pay for it. But then governments essentially do something called taxing people. They tax people, and those receipts that are collected are used to create these systems and hopefully deliver them in an efficient way to the public. It's not always the case, but that is the theory behind it. So on one end are private goods. These are public goods, which are often delivered by the government. But there are in-between cases here. Imagine if there are many users of a system, but they're willing to pay if you were able to charge them properly for it. For example, imagine a toll road. Somebody has to build a toll road and somebody has to pay for it, pay for the construction, pay for the maintenance and everything. And all the chemicals that go in there and the service and the construction costs and all that. But the total costs have to be somehow paid for. Now, the concept of toll roads is that you essentially charge a toll to anyone who uses that toll road, and therefore there are many users, but they are willing to pay for the service that is offered by the toll road. Those are, in concept, they're called toll goods. And many a times, local governments, state governments and local organizations end up constructing these. There are exceptions, but broadly, that's what happens. The last case is the most trickiest case, and this is where Elinor Ostrom did most of her work. This is the case when you have a single user of a particular product or a service, and they are not willing to pay. Because you see, they don't realize that by their use of that system, it impacts everyone, but they can get away with it. They can, in essence, not be charged for things that they are extracting from the system. For example, let's say you have groundwater that is being pumped. When you pump groundwater in your own property, the groundwater comes from all sides. So it may come from the neighboring property. And unless it is really well monitored and you have an agreement with the next door neighbor and it is properly measured and priced and so on, it's really difficult to manage this resource called the groundwater. This resource, this kind of a resource, is called common property resource, or a CPR. In fact, most of the time, until Elinor Ostrom came along, a lot of people found that these resources get abused and ultimately exhausted to the detriment of the entire pool of people who should be using that resource in a sustainable way. For example, take the groundwater example, where people who actually extract that groundwater, and if everyone starts doing this, nobody is accountable to anyone for it. Ultimately, the groundwater goes down like it has in so many parts of India and the rest of the world, and nobody is really accountable for it, and ultimately the resource goes down and everyone suffers. This is called Hardin's paradox in economics. It's important for engineers to understand that in fact just providing a pump, for example, as a technological solution doesn't necessarily provide the long-term service that it is intended to provide, because you are drawing down on the resource. Similarly, in our case, the resource is the ozone layer. And the ozone layer needs to be protected. Otherwise, we have catastrophic effects. We can't draw it down. We can't emit these ozone depleting chemicals on and on forever until the ozone layer disappears and everyone suffers terribly. So what was needed in place of that, or to manage that common property resource, was a mechanism and an institution. And that institution, just like you have private sector to manage private goods, the government to manage public goods, you have say local governments to manage toll goods, what you need is a system with which we can try and manage and control the emissions that of the ozone depleting substances. That system, okay, is the Montreal Protocol. That system allows all these players, the private sector who produce these ozone depleting substances, the government which regulate these, the toll goods. So in fact, the World Trade Organization, which sets the standards and rules for trade of these materials. Okay, and even in all these, engineers are needed. The engineers are certainly needed in producing it. The engineers are certainly needed in regulating it and in creating standards for them and monitoring the ozone depleting substances. Engineers are needed in setting the transport standards and the packaging and the monitoring that's needed in the trade of these substances. And engineers are also needed so that in the Montreal Protocol, we could actually measure, monitor, and enable the common work that needs to happen so that people can cooperate towards reducing the production and consumption of these ozone depleting substances. This is the difficult task at hand. And that is what the Montreal Protocol was able to achieve despite its complexity, and therefore the success of it was that from over 20 million tons being generated per year, only a few thousand tons are now being generated here. Now, where did the engineers start playing a role in this? As a part of the Montreal Protocol, which incentivized the generation of alternatives. So more science, more engineering to come up with alternative substances which could replace the functions that were being performed by these ozone depleting substances. A lot more work on this needs to be done, but we are making tremendous progress because of the role that Montreal Protocol has played in this. Now, what's important for engineers to understand is that when you do engineering, it's important in all these different cases, the private goods, the public goods, the toll goods, and the common property resources. This is where we fit into the world. And what is important therefore to ask, and many a times we engineers, we are given a problem and we end up solving it, and we solve it very well. But very rarely do we get a chance and an opportunity to step back and say, why are we doing this in the first place? Why should we be practicing good engineering? And the answer lies in the history and the structure and the effort and the success of the Montreal Protocol, which tells you how important it is that the work we do is responsible not only for our careers and our work, but for the world that we live in, and to ensure that we can have a sustainable and resilient lifestyle going forward with growth and with benefits to all. Again, I want to thank Banasthali Vidyapith, the Department of Chemical Engineering. I'll leave you with these thoughts, and with thanks to my dear friend, Dean Natarajan, for giving me this opportunity to speak with you. Thank you and good evening.